Okay, here we're going to do chalk. We're going to do an example that sort of gives us a visual intuition for inclusion-exclusion. Okay, so like the formula we saw for inclusion-exclusion, which seems like a little bit counterintuitive, and we're going to go through it here and explain why that formula actually holds. So the formula for inclusion-exclusion, let me make sure this is on the screen. Yeah, formula for inclusion-exclusion, I have probability of A union B. Okay. Recall that A union B in English means A or B, right? So it's also inclusive, so it means A occurs, or B occurs, or both A and B occurs. So I think of it as at least one of A and B occurs, right? It's either one or the other or both. And we saw that the formula for this is probability of A, margin B, plus probability of B, and that makes sense, right? That's intuitive, like probability of each of them. The weird part is we have this minus the probability of the intersection A and B. Remember, intersection means both A and B occur. And this is kind of the part that it's kind of tricky. We're not totally sure what it means, and that's what we're going to try to address here. Okay. So we're going to think of this visually in terms of a Venn diagram. So what I want to do is I want to imagine A and B as a nice little Venn diagram. Here's A, here's B. You know, a Venn diagram you've seen 1,000 times. This is the part of A that's not in B. This is the intersection of A and B, and this is just B itself. And I want to think of this in terms of a sample space. We call the sample space omega. So that's a Greek letter for omega. Don't worry, like this notation seems weird, don't let it throw you. The idea here is we want to think of probability in terms of this visual world. Think of this entire sample space as having area 1, right? So it has probability 1. Like probability 1 that something will happen. And then you can think of these like sort of smaller islands within the area as like the larger they are, the higher the probability that it occurs. So think of like this entire area as probability 1. I put a point down randomly, right? And if it lands in the A circle, then A occurred. So it makes sense that if A is bigger, right? If A is larger, it has more probability because putting a random point down is more likely to be in A. It just takes up more of the sample space. So if A has area 1/2, then probability of A is 1/2, right? If I put a random point down, it's a 1/2 probability that I land in A in this entire sample space. This is a way to like visually think about probability. It's kind of analogous to what we've been saying earlier. And now we can think about probability of A union B given this sort of setup. So probability of A union B. Let's probability of A union B, right? At least A or B occurring. We want this total area, right? We want all the area that's encapsulated by at least A or B. So let's think about what this formula does. First, we add probability of A, right? So we add this. The entire circle of A. And then we add the probability of B, right? So we added the shading of B circle. And like you probably noticed, the crosshatch in the middle, we double counted the intersection, right? We added the intersection twice because by definition it's in both A and B. So we added it twice. That's why we had to subtract it out once, right? We added it twice. We don't want that, right? When we do this addition, when we add P of A and P of B, we get more area than this entire circle. We just want the area of this region, right? So we have to subtract that out once. Okay. You think of this in some corner cases, like if A and B are disjoint. So here's a Venn diagram where A and B are just disjoint. They're not overlapping, right? Here we have P of A plus P of B minus P of A and B. But in this case, P of A and B is 0, right? Because there's no overlap, so we're not subtracting anything, so it's fine. So that works. What if we have that A and B are the same event, right? So let's imagine like two circles on top of each other. Well, in that case, we have P of A plus P of B. Since they're the same event, A and B are the same, so it's P of A plus P of A minus P of A and B, which is just P of A and A. Same. Basically, we're adding the same circle twice, and then we're subtracting that circle, so we get the circle once, which is exactly what we want. So it kind of works in these corner cases as well. Grab an eraser. Okay, so the last thing we want to think about is we get this in the two-dimensional case. We get this in the two-dimensional case. We want to see how it extends to the n dimensions, as we mentioned with inclusion-exclusion. Think about a nice three-way Venn diagram. Let's see if I can draw it. Okay, so we have A, B, and C. And think about, again, finding the union, probably the union of A, B, and C. We're going to add this A circle, so I'll start to draw the A circle, right? Then we have to add the B circle. Then we have to add the C circle. And already, like, you can see it's kind of a mess, but this like double, this A and C double we added twice, this B and C double we added twice, this A and B double we added twice, we added the triple, the middle intersection 3 times. So we need this like adjusting, like kind of rotation back and forth. It's easy to visualize in this case. If you go through, I think it's good practice to go through, think about it in the case of 3. And the idea is that it continues to generalize as we get n of these circles. We get, the singles, the doubles, the triples, right? And we're alternating adding and subtracting. So that's the visual intuition behind inclusion and exclusion. I think it makes a ton of sense when you actually draw it out. As they say, picture is worth 1,000 words.